big news for the GPCR community. Discovery on Target is happening September 22nd to 25th in Boston, Massachusetts. Hello, everyone. Yamina here. Welcome to the Dr. GPCR ecosystem. We're partnering this year with DOT to spotlight their exciting program, and in today's video, you'll meet one of the incredible presenters. You'll find all the details and links in the description. I'll be there in person chairing a session, and you won't want to miss Dr. Terry Kanakin's talk on the kinetics of allostery and his short course on the 4 most common causes of drug candidate failure. And remember, Terry's Corner is always available with on-demand pharmacology courses you can access anytime. Plus, GPCR Happy Hour is happening on September 24th. Your chance to connect with colleagues, share ideas, and catch up with friends in a relaxed setting. Find all the links in the description. And now, let's dive in. Hello, everyone. This is Yamina from Dr. GPCR, and today I'm excited because we're doing something very unique with our friends at the DOT at Discovery on Target, held in September here in the Boston area. I'm joined today by Dr. Aaron McGrath. Aaron, welcome.
Thank you for having me.
I'm very excited to have you on. So why don't we start you off with a quick introduction? Tell us who you are and what do you do?
Yeah, that would be great. My name's Aaron McGrath. I'm a structural biologist at Takeda Pharmaceuticals, based in Cambridge, Massachusetts. Associate director here. I'm a structural biologist, and I've been here for about 5.5 years now. Interesting fun fact is I moved to the Boston area about 6 weeks ago. And before that, I'm obviously from Australia, born and raised in Sydney, Australia, where I attended university. And another fun fact is until I joined industry, I had never worked on any GPCRs. So there you go.
If this was a regular podcast recording, that would have been one of my questions. When did you first start working on GPCRs? But you've already told us that. So tell us a little bit more about the work that you do, and more specifically about the work that you're going to be presenting at the Discovery on Target meeting.
Yeah, of course. I mean, like any other big pharma company, we're looking at all sorts of interesting targets, different sorts of folds, different sorts of modalities. But you know, every now and then we still work on GPCRs. So one of the things that has been really interesting for me over the last few years was the work that we were doing on a really unique type of Class A GPCR known as the PARs, the protease-activated receptors, and really unlike any other sorts of GPCRs, they're a fascinating flavor just in the way that they're activated. So unlike the predominant number of GPCRs that you would have heard of that bind soluble ligands, the PARs are activated, as their name suggests, by proteolytic cleavage at the N-terminus that reveals what's known as a tethered ligand within that N-terminus, which folds back and self-activates the receptor. So we did a lot of structural biology on these targets, really looking to unravel how this happens and the differences between the inactive and the active states of the PARs, which we thought was really fascinating for a couple of reasons. Namely, there are some unique differences for the PARs, namely the orthosteric site is very shallow. And we don't tend to see the typical sorts of large TM6 movements when they're activated that you would typically find in GPCRs. And that was really one of the most notable things that we noticed in our structures, and something that we published recently. So we're talking a lot about the activation mechanisms of PAR1 and PAR2, and really pointing towards the idea that this is most likely a unified activation mechanism across all 4 human PARs. And then looking at some of the challenges that this narrow and constricted orthosteric pocket has presented in drug discovery, and really is born out of the structural features that we noticed. And so there's still a lot of work to be done on the PARs to fully realize their potential as the drug targets, the attractive drug targets that they are to treat a whole host of diseases such as inflammation and cancer and other sorts of disease states that the PARs are implicated in.
That is so interesting, and I do remember reading quite a bit about the PARs, and depending on which protease cleaves the receptor, you get a different, or the length of the cleaved portion changes. What in your work have you looked at these differences from a structural perspective? How do those cleaved portions affect the receptor structure? Is there any structural difference in there?
Not per se from our structural work, but that's a fascinating characteristic of the PARs, really looking at the amount of flexibility they have depending on the different proteases that are available, and really linking the availability of proteases to intracellular signaling and turning the 4 different PARs on using the canonical proteases, but non-canonical proteases as well. So there's a lot of flexibility, and that really hints back to the therapeutic potential of the PARs being, really important in multiple different signaling pathways.
And also to the conformations, the consequences in the conformation stabilized in order to activate the signaling pathway. So depending on which protease cleaves, I'm assuming that the receptor would have a separate conformation that would then translate into a different signaling pathway, which I find very fascinating. And to your point, having the receptors in different environments exposes them to different proteases, and that's where the diversity in signaling comes from.
Yeah, and when I first started working on the PARs, I was really just intrigued by the idea that this links protease activity to interest via GPCRs. So that's what makes this particular family of Class A GPCRs really, really fascinating.
Wonderful. In your experience working on GPCRs and on the PARs, what are some of the challenges that we have overcome over the years and some of the challenges that we still are looking to overcome?
I mean, as a structural biologist, of course, it's an exciting time to work on GPCRs. I don't think we need to go that far back in the history of structural biology of GPCRs to see the tremendous heroic work that was done by crystallographers, namely, around 2010. There's really heroic examples of campaigns to structurally determine GPCRs in all sorts of different states. So that in itself was just an exciting period for GPCR structural biology. But of course now, not many crystals are being grown for GPCRs with the advent of the resolution revolution. And certainly here at Takeda, something that we're really interested in now is leveraging cryo-EM to look at fully activated complexes of GPCRs in their active state, be it with their endogenous ligands or with potent small molecule chemical matter or peptides bound to the orthosteric pocket and then bound to heterotrimeric G proteins. And that's all done with cryo-EM microscopes and a significant investment in cryo-EM, which is not something that I ever thought that I would see. The tractability of structural insights into GPCRs and really leveraging structural biology in real time to drive drug discovery campaigns forward using structure-based drug design. So really, in terms of challenges, we've overcome so many, but there are still challenges to overcome. I think it's a really sweet spot at the moment for cryo-EM for agonists, so fully activated complexes with G proteins bound. But of course, antagonist programs as well are really, really important for a lot of different targets, including the PARs, and then really looking at making it more tractable and more routine to solve structures of inactive forms of GPCRs, most likely using cryo-EM, and really pushing the technique to make it routine to determine antagonist-bound structures as well. I think that's the next big challenge and something that in the future will become routine. And I think we're right there in terms of the technology and the insights that we've made to date.
Wonderful. And I think you're right. We got to a point where getting a structure for your receptor with the G protein and with your favorite molecule isn't, I mean, it's costly, but it's not impossible anymore.
No, and with that comes a tremendous amount of data and a tremendous amount of insights. And one other thing I think that's really interesting, and it's happening right now, is the insights that we're going to gain from AI and ML, of course, with all this structural data that we have, and the ability to really move the needle in that regard for, particularly in the drug discovery space, but I think in GPCR biology in general is really going to be the benefactor of all this structural data that is continually being produced as part of these, tremendous leaps and bounds that have been made in the field in the last few years, particularly.
No, I agree. I agree with you. I think the biggest challenge will be building out those systems that speak to each other. The in vitro assay, the cryo-EM, the machine learning, the docking. Absolutely. Not in a way that people understand what others have been working on, but also feeding that information to the machine learning algorithms. That's the biggest challenge.
Yeah, I think as structural biologists in particular, we're very reductionists. We break things down into pieces that we can modulate and that we can work with and make them kind of fit the technique that we're working with. And I think even through cryo, looking at things in more of a wild type state rather than a crystal lattice has been tremendously informative in terms of the dynamics of these molecules. But to your point, then bringing in all of these other techniques and looking at it in terms of more of a holistic picture of how these molecules engage their ligands or engage a small molecule within a cellular context, that's the next big step. And I think AI and ML will really tie those, very different techniques together to give us a more holistic overview of a target.
Exactly. And to your point, having all of this data curated, you also want to control what goes into that machine learning algorithm, because
Yes.
garbage in, garbage out.
Yes.
Yeah.
So that we're training it with high quality experimental data and really reaping the rewards of that in the future. It's very, very valuable information and an exciting time. So let's see where we get to.
Absolutely. I look forward to your talk at the Discovery on Target meeting this year. Thank you so much, Aaron, for your time. Don't go anywhere. We're just going to stop recording.
Thank you.
Thank you.
I can't wait to see you in Boston for DOT 2025, especially at the GPCR Happy Hour on September 24th, where we'll connect, exchange ideas, and unwind together. And don't forget, Terry's Corner is ready when you are, with on-demand pharmacology courses. Check the links below for all the details. Until next time, this is Yamina, signing off.